Hello, everyone. Welcome to the March 31st edition of Math Stats. Couple reminders, you have a homework 6 due on Friday, and keep collecting survey data. Keep pestering those friends of yours who are math majors or science majors and have not taken the surveys yet. All right, so today we're going to talk about what is in section 8.5, which talks about power. This is not the kind of power that comes from the physical concept. This is talking about the power of a statistical test. So thus far, we've done a lot talking about alpha, which is the significance level. So thus far, we've talked a lot about alpha, which is the significance level. Or it's the probability of a type 1 error. Remember, a type 1 error is where the null hypothesis is true, but you reject it anyway. So beta is the probability of a type 2 error. Remember, a type 2 error is where you do not reject the null hypothesis, even though the alternative hypothesis is true. So to illustrate how we're going to compute some type 2 errors, we're going to follow example 8.5-1 in the book. Because I think this example really illustrates what we want to know. Okay, so assume that when a person gets a quarter and places it on the table, they can either put heads up or heads down. And let P be the probability that the quarter is placed heads down or tails up. So we're going to test the null hypothesis that the probability is equal to 0.5 against the alternative hypothesis that P is actually less than 0.5. So we're going to take a sample of 20 people. And we want to count how many of them place the quarter face up and how many put it face down. Well, this is a Bernoulli, each of these is a Bernoulli random variable. Remember that a Bernoulli random variable is one that has two outcomes. And we're going to say, so these Bernoulli random variables were x1 up to x20 because there were 20 people. And we're going to say that xi equals 0 implies that the person placed the quarter heads up. And we're going to say that if it were equal to 1, that means that the quarter was placed tails up or heads down. All right, so this is our setup. And our test statistic is y, where we just add up these Bernoulli random variables. And we see that this is a binomial random variable with 20 trials and probability p. Okay. So we're following the book. We're going to set the critical region to equal all the outcomes where y is less than or equal to 6. So what we see is that, well, y is binomial. So under the null hypothesis, that's where we assume p is 0.5. The probability of having y less than or equal to 6, this is going to be the probability of the type 1 error, is the sum of all these entries. And if we add that up, we find that it's roughly equal to 0.0577. And we can compute that using RStudio if we want. Here we see that the calculation we're doing is p binom of 6, 20, and 0.5, and we see that we get the alpha value that we expected to get. All right, so let's go back to our work. Now, that's the probability of a type 1 error. So in order to calculate the probability of a type 2 error, you need to actually know what the true value of p is. So let's compute beta, the probability of a type 2 error, when the actual probability is 0.35. So beta is equal to the probability that y is from 7 to 20. So you remember a type 2 error is when the alternate hypothesis is true, but you do not reject the null hypothesis. So the alternate is true, but you don't reject. That means that y was between 7 and 20. We got between 7 and 20 quarters tails up. So this is equal to the sum from y equals 7 to 20 of 20y 0.35 to the y 0.65 to the 20 minus y. Or if we want to use the built-in feature, we can do 1 minus the sum from y equals 0 to infinity, or 0 to 6 of the same PDF, because this is the complement of that. So we can use RStudio to help us out here. And what we can do is we can do 1 minus p binom of 6, 20, and 0.35. And we get a value of 0.5834. That's pretty big. That's a gigantic type 2 error. That means the odds are you're going to have a type 2 error. So let's try it again. Let's try again, except now let's assume that the probability was actually only 0.15 that we place a quarter tails up. In this case, we compute the probability of the type 2 error again. Except this time we assume that p was 0.15. And just like last time, we can compute this a very similar way. And we can do this on RStudio. And we get 0.022. So this is equal to 0.022. That's a much more reasonable type 2 error. It means that if our true probability is 0.15, there's only a 2% chance where we do not reject the alternate hypothesis. When we do not reject the null hypothesis. Okay, so instead of considering the probability of accepting the null hypothesis when the alternative is true, we can compute something similar. So we have this new value k, which is the probability of rejecting the null hypothesis when the alternative is true. Observe that k is 1 minus beta. And we're going to construct a function for k. So we observed before that it depends on our probability of success. So what we know is that k of p is this sum. So this function k is called the power function of our test. It's basically telling us, okay, what's the probability that we reject the null hypothesis when the alternative hypothesis is true? So we also can see a few things. Alpha is actually equal to k of 1/2, which is about 0.0577. We also observe that 1 minus k of 0.35 is 0.5834. This was beta in an earlier example. And in a different example, 1 minus k of 0.15 is 0.022. So knowing beta, the probability of a type 2 error, and knowing k, the power, those are equivalent pieces of information. So the value of the power function at a particular value p is called the power. Okay, so a good power function has small values when h0 is true and large values when p is very different from 1/2. Okay, so let's actually graph the power function now. All right, so I've graphed the power function, and you see that it goes from basically 1 when x, our probability, is 0, all the way down to pretty close to 0 when p is 0.5. In fact, the exact value we know is 0.0577. So we'll talk about that more in a second, but you can graph it and you can see what happens to the power function as our alternative hypothesis changes. So here at 0.4, well, we don't really have the, our power function is not that big, so we don't have that much power. By the time you get to 0.2, you have a much bigger value of the power function, which tells us that the probability of a type 2 error is getting pretty unlikely then. All right, so let's go back to here. And we can talk about another example. So, before we do that, though, let me just make a quick remark. Our power at 0.35 was 0.417, and our power at 0.15 was 0.978. And so you see that the power goes up as the probability goes down for this problem. Okay, now we need to do an example with the normal distribution. Okay, so we're going to take a random sample of size n from normal distribution with unknown mean and variance 100. This is going to be test scores on a statistics test. That uses computers. The old class did not use computers. We want to test whether the computers help or not. So in the old exam, the average was a 60. But on the new exam with computers, we want to know, does it improve the score? So we're going to use a sample of size 25. And our test statistic is going to be X bar, the sample mean. And our critical region is going to be the range where X bar is bigger than or equal to 62. That's our critical region. That's where we will reject the null hypothesis and accept the alternative hypothesis. So what this tells us is our power function is equal to the probability that X bar is bigger than or equal to 62. Now, we know that X bar has a normal distribution with mean mu and variance 100 over 25, which is the sample size. So what this tells us is this probability is the probability that X bar minus 62, or sorry, minus 60 over 2 is bigger than or equal to 62 minus 60 over 2, assuming that mu is true. And this is the same as 1 minus phi. So all contesting values so this is the CDF of the standard normal. Okay. Okay, so let's do a couple of them in RStudio, and I think you'll get the hang of it. So let's share RStudio. So let's calculate what we need to. We need to do 1 minus p norm of 62 minus 60 divided by 2. And we get 0.1587. And then we'll do the same thing with 61. That's 0.3085, 62, 0.5, 63, 66, and 67. So let's record these values in the table. We get 0.1587, 3085, 500, 6915, 9772, and 9938. So we notice this as the mean goes up, the power goes up. And that makes sense, because if our true mean is a lot higher than 60, it's going to be pretty likely that we reject the null hypothesis. But if our mean is very close to 60, there's not much of a chance. There might be a very big chance that we commit a type 2 error. That is, we accept the null hypothesis, even though the alternative is true. So let's graph it and see what this looks like. So all right. So here we see that the value of our power goes up as our mu goes up. That makes sense. So what we see here is we're going to annotate this a little bit. This distance right here is the value of alpha, the significance level. And this distance, well, excuse me, let me fix that slightly. So here's 1. That's 1. This distance is beta. Excuse me. And this distance is the power. So this is the power. So you can see how this graph corresponds to those different concepts that we've learned about. So here we saw, if I go back to my whiteboard, we saw that alpha was about 0.1587. Typically, we want alpha to be 0.05. So we need to adjust our critical range in order to get alpha equal to 0.05. So let's adjust our critical range. Okay. So we know that in order to do this, we need to look at the null hypothesis. And the null hypothesis, we know that 60 is the mean under the assumption of the null hypothesis. And we don't know what this cutoff value is going to be, but we know it must be equal to 1.645, because if I go to RStudio and I compute Q norm of 0.95, it's 1.645. That's the standard score of the 95th percentile. All right. So we solve for C. To get C equals 63.29. All right. Well, let's find our new power functions. So what this is telling me is that my new critical range is x bar is bigger than 63.29. So what I find is that my new power function should be 1 minus the CDF of 63.29. minus the mean over 2. Now, if I plug in k of 60, what I will get is 1 minus p at p norm of 63.29 minus 60 divided by 2. I get basically 0.05, just like I expected. What if I do k of 66? I get 0.9 123. So let's compare that to what we had before. Before, whenever k was 66, our power was 0.9772, 98% almost. But now it's down to 91%. So what we noticed was that when we decreased our alpha, our beta, so here beta will equal 0.0877. Okay, that's bigger than the probability of the type 2 error was before. So in general, without changing the sample size or the type of test, the hypothesis, a decrease in alpha causes an increase in beta, and vice versa. So here's an important remark that you should know about testing. In general, and a decrease in alpha causes an increase in beta, and a decrease in beta causes an increase in alpha. The only way to lower both alpha and beta, that's the probabilities of the type 1, type 2 errors, is to increase the sample size. All right. So we're going to do that and see what happens. We're going to increase the sample size to 100. Okay, so what happens? Well, what's changed is that X bar has a smaller variance now. In fact, the variance is just 1. So we want to obtain alpha is 0.05. So this tells us that whatever our critical value is, minus 60 over 1 must be 1.645. So our new cutoff, our new critical region, comes at 61 0.645. So C is the collection of X values bigger than 61.645. So, assuming our alternate hypothesis is true, our probability of a type 2 error well, let's find out what this is equal to. Wow, that's small. So let's see if I can write this all out. It's 0.0000665. That's small. And so we see here that we've decreased alpha and beta simultaneously. Okay. And observe that the power here is 1 minus this. All right. So that's fine and all, but what if we don't want to guess about the sample size? What if we want a way of finding it when we specify alpha and beta? So this is going to require setting up two equations and two unknowns. So let's set the following example up. We're going to want alpha equal to 0.5 again. And we know that's the probability that x bar is bigger than or equal to c, assuming the mean is 60, which is 1 minus phi of c minus 60 over 10 over root n. So let's say we also want beta to equal 0.05. Well, that's the probability. Well, it's 1 minus the probability of x bigger than or equal to c, assuming mu is 66 in this case. So that's phi of c minus 66 over 10 over root n. All right. So we need to find some z-scores. And so it's called. So for alpha, we see that we need to have c minus 60 over 10 over root n equals 1.645. Because this is the 95th quantile. And for beta, we see that c minus 66 over 10 over root n must be minus 1.645, the fifth quantile. So solving for c, we obtain c equals 63. And then we plug that into here, and we get 63 minus 60 over 10 over root n is 1.645. This tells us that 3 root n over 10 is 1.645. Shows that root n is 1.645 times 10 over 3, which tells us that n is 1.645, 10 over 3 squared, which is roughly 30.1. So we need n to be bigger than this, so we can pick n equal to 31. All right. So that's how we solve for n if we have a specified value for our null hypothesis our simple alternative hypothesis and our probabilities of type 1 and type 2 errors that will let us find the sample size we need. So I'm going to give an example, and we're going to work this in class on Tuesday. So here's the example. Assume, so go ahead and write this one in your notes so you have it, but don't actually solve it. Assume that SAT math scores of students who attend small liberal arts colleges is normal with variance 8100. We're going to test the null hypothesis. The average is 530 against the alternative hypothesis that it's lower than 530. So we're going to have a sample size of 36. And we're going to find the critical region to be sample mean less than 510.77. So first thing I want you to do on Tuesday is find the power function K of mu of this test. What is the value of alpha? What is the value of K of 510.77? So I want you to adjust the critical range so that alpha 0.05, but don't change the sample size yet. Using this new critical range, compute the new value of beta, the type 2 error. And last but not least, find the critical region and sample size so that alpha and beta are both 0.025. Let me know if you have any questions, and I'll see you all on Tuesday.